About 4 years ago, the LIGO observatories reported the detection of gravitational waves from the collision of two black holes. And as you may well know, this led to the Nobel Physics Prize in 2018. And in just 4 years, we have gone from excitement to now the construction of an ever-increasing catalog of black hole mergers. Now, we are no longer thinking about whether we are going to detect gravitational waves. Rather, we are thinking what are the astrophysical properties we can infer from this catalog. And this has to do with the mass and spin distributions of black holes and how these are related to the formation channels that lead to these objects. And as you can infer, this has obviously implications for stellar evolution. Beyond black hole mergers, the LIGO and Virgo detectors also reported recently, well, 2 years ago now, the collision of two neutron stars. And this is now a different type of source because in addition to producing gravitational waves, it also produces electromagnetic waves. And this is a beautiful astrophysical source because it provides information not only about the source, but also the astrophysical environments. Now, this is all, really exciting. Gravitational waves provide the means to see the dark sector of the universe. We cannot see it with electromagnetic observatories, but now we can listen to it with LIGO and Virgo. On the other hand, when we have electromagnetic or astroparticle counterparts, we can also see the electromagnetic waves and neutrinos. If we are really lucky, as we have been with LIGO, Virgo, and very soon with Kaga in Japan, we get to see a core collapse supernova. Then in our backyard, obviously in the galaxy, we will also feel these cosmic messengers with neutrinos. Now, all of this is really exciting, and all of these different messengers now have given us new powers to observe the universe, and this is multi-messenger astrophysics. Now, one aspect of my research group has to do with objects that form in dense stellar environments. And here we're talking about black hole or neutron star systems. And it just happens that because of the many interactions that they have with nearby black holes or stars, their orbits are really interesting. They are a little bit elliptical. Now, if we think about the kind of sources that LIGO is detecting, based on their masses, we do understand that we are going to see the merger and ring down of this type of gravitational wave sources. And if you want to understand the physics of these eccentric black hole mergers, then you cannot rely on analytical relativity, because that's good to describe the evolution when the objects are far apart. So we need numerical relativity. And so in our group, we have been using open source software stacks like the Einstein toolkits to produce waveforms. And here you are seeing waveforms that represent the mass ratio given by that parameter Q, and the orbital eccentricity given by that parameter E naught. And as you can see here, for a given mass ratio, as you increase the eccentricity, the waveforms change quite a lot. So it is not a parameter that you can average over or integrate and then you get rid of it. It is going to affect the dynamics dramatically. And as you can see, the catalog that we present here covers a broad range of mass ratios. And if you're a numerical relativity expert, you know that as the mass ratio increases, then it is harder and harder to simulate these sources. But we managed to produce waveforms up to mass ratio 10, the first of their kind in the literature. And we also studied what happens when you include higher order modes. That means beyond the quadrupolar approximation. And as you can see here, they have also dramatic effects in the topology of the waveforms. And we have also explored the implications of these results for the detection of these sources in the LIGO context. You can go and check this article. Now, this is all beautiful. You can see that this is a magnificent convergence of different areas of research, experimental physics, building the LIGO detectors, using supercomputers to understand the physics of these sources with numerical relativity, but also using supercomputers to process the data gathered by these detectors, and then inferring the astrophysical properties of gravitational wave sources. And then combining these as rapidly as possible with electromagnetic observatories to do multi-messenger astrophysics in real time. And obviously, we need theory to interpret these observations. In different words, are we looking at the collision of two black holes or two neutron stars, or maybe two low-mass stellar mass black holes that somehow mimic neutron star collisions? So we need theory to understand this. And as you can see, we have been able to bring together these disparate areas of research to make these discoveries. Now, as we look ahead in time, all of this is great. But what is happening right now with the LIGO and Virgo detectors, with enhanced sensitivity, we are seeing a lot more sources than in the 2 previous observing runs. So just to give you some numbers, in O2, the second observing run, we detected a source on average for every 15 days of search data. But as the LIGO and Virgo detectors continue to enhance their sensitivity, we may detect sources every 15 minutes. Now, you know that we detected a lot of black hole mergers around the detection of the first neutron-star collision that we only made publicly available months later, right? Now, with better equipment, better resources, the question is, will we be able to cope with the pace and latency of discovery? Because multi-messenger astrophysics requires real-time action, right? So here we have, the opportunity to innovate, to try to change the computing paradigm that right now is being used by LIGO. And obviously, just quoting Thomas Kuhn, when a paradigm shift is explored, obviously there will be reactions from many stakeholders. Those that have been invested in developing the tools that are established will not react happily when you try to do something new. But they are essential because it just happens that the party that is represented here as the conservative ones will give you all the information you need to develop a robust, bulletproof paradigm. And we have been learning a lot from our colleagues, not only in LIGO, but also in astronomy, to try to convince them that deep learning and HPC provide the means to increase the ability to detect gravitational waves in real time and at a scale. So let me tell you how this has been happening. Acknowledging that we're going to be detecting a lot more gravitational wave sources in the near future, we have been exploring how we can leverage all the activities that are happening in industry and technology, harnessing the big data revolution, basically deep learning to process big data sets in real time at a scale. And there you can see this box, end of Dennard scaling. It just happens that when the HPC community started this period of crisis, the big data revolution started to skyrocket. And now they are no longer 2 different identities or, if you want, communities. Now people don't talk about HPC, but about HPCD, right, where these data. So it is a major change in how we are doing computing. And this is just going to accelerate its development in the near future. So what I have been doing with my students at NCSA is the following. We have been using HPC for traditional studies, like numerical relativity. But at the same time, we're also using HPC to produce data sets to train neural networks. And these data sets are basically waveforms. And then once we have these data sets, we train the neural networks at a scale using hundreds of nodes. At the same time, we're also exploring the use of innovative hardware architectures. GPUs, as you may know, are the main engine for the revolution in the big data era. And so when you combine this, the ability to produce data sets at scale, you use GPUs to train deeper models with ever increasing larger data sets, then you can go and try to explore what happens when you have these neural network models. And what we have found is that if you go and process LIGO data, we can go through about 4,000 seconds of data in 1 millisecond. And let me just walk through this series of events. In January 2017, we presented the first generation of these neural network models. It was a basic neural network, and we were able to show that if we consider just a 2-dimensional parameter space that describes the masses of the black holes, then we can go and see the sources that LIGO had detected, not with a supercomputer cluster, but with a single GPU in real time. And this was using simulated noise. There was a need, obviously, to demonstrate that this could work using real LIGO noise, and we did that in November 2017. And around that time, a completely independent group took our papers and they reproduced our results. In a simplified case, using just classification, or if you want detection, using simulated noise. But it is good that by just looking at all the information that we provided in these papers, independent groups were able to reproduce these results. Now, it was obviously necessary to go beyond a two-dimensional parameter space. And in a more recent paper, we are doing this for a really deep signal manifold, as I'm going to show you in a little bit. So in summary, what has happened? Well, let me introduce you to Daniel George. He was my first grad student in my group. He's now in Google X. But the first thing that we did, this is exploratory mode, is consider a two-dimensional signal manifold. This is a small training data set, about 4,000 waveforms that cover the parameter space that LIGO can study. And so we showed that with this simple model, we could not only observe signals produced by black holes on circular orbits, but also the more complicated signals that I showed you before, the eccentric ones, and also signals that describe black holes on circular orbits, but whose spins are precessing. So these waveforms are really complex, and still the neural network was able to detect them. In different words, the neural net had the ability to extrapolate to new kinds of sources. This is really exciting. And as I said, about a year later, some of these studies were corroborated by these colleagues. Now, as I said, demonstrating this for a two-dimensional signal manifold is cool, but what about doing this at a scale? So the next question was, okay, let's consider black holes that are astrophysically motivated on circular orbits, but that have spins. Now the parameter space is not as simple. Now we have a four-dimensional signal manifold. We are no longer using 4,000 templates, we're using 1 million templates. And the neural net is much deeper. And there are things that you need to consider when you're doing the training. One is the neural net needs to process data as it is coming in, so you need to ensure that the neural network is time invariant. That means you can see a signal wherever it is in the data stream, but it is also scale invariant. That means it doesn't matter what signal-to-noise ratio the signal has, it should be able to see it, and that is the scale invariance. So incorporating this information in the neural net, we were able now to go and process LIGO data. We identified the 10 black hole mergers that LIGO has reported. But as you may know, when you're doing parameter estimation in LIGO, this study takes from several hours to days, if not even months. We were able to complete this study in milliseconds using 1 GPU. So this is the new ability or capabilities that you get from deep learning. You can do this analysis at scale and in real time. So there we are. Now we have a spin in the neural nets. And just to show you some results here, for each gravitational wave source that you see here on the left column, we have these different parameters. The masses that represent when the black holes are spiraling into each other, the final spin of the black hole, AF, and then we have two frequencies that we call quasi-normal frequencies, omega r and omega imaginary. And these two describe basically the real part of the quasi-normal frequency, how fast the waveform is oscillating around merger, and then the imaginary part is the damping time of the waveform. So in a single neural net, we are estimating the parameters of the source before and after merger, but we also give you the ability to test general relativity, because it just happens to be the case that the last three parameters that you see there are the fingerprint for the identity of black holes, based on black hole perturbation theory. And the three columns here represent the mean standard deviation, and the skewness. And all of these results are consistent with the more compute-intensive Bayesian analysis that LIGO colleagues use. So this is really good. It is now a production-run pipeline. Now, talking about, again, the convergence of all these different pieces, we are using advanced LIGO noise as the input to train these models. We are using blue waters to produce the data sets to train the neural network models, and obviously the information we get from numerical relativity, because when you are designing these models, the neural network models, you have the freedom to choose the loss function, for example, to optimize the neural net. And all the physics insights that we get from these simulations is what is used to train these algorithms. So there you are. This is brought to you by NCSA and Blue Waters. Now, I'm just going to go briefly on another cosmological application of neural nets. And this has to do with gravitational wave cosmology. So many years ago, Bernard Schutz predicted that we could use gravitational waves to measure the Hubble constant. Now, we no longer use an electromagnetic counterpart. We only use the gravitational waves produced by the black hole mergers. And then you need to do some statistical analysis to figure out the host galaxy of this black hole merger. So in different words, if you want to do gravitational wave cosmology, you also need galaxy catalogs. How do we go about this? Well, SDSS, the Sloan Digital Sky Survey, is a beautiful example of this. They recruited astronomers and people that were willing to classify a ton of galaxies. So citizen science is beautiful, but if you look at the dark energy survey, you are going from about 1 million galaxies to 300 million galaxies. So this is no longer scalable. We need something else. And what I have done with some of my students in my group is the following. Let's use one of these neural nets that is state-of-the-art for image classification, that is trained with ImageNet, which is a human-labeled image data set that has about 1 million images that encompass about 1,000 different classes of real object images. You train a neural net using this data set, and you get a model called Exception that is the state-of-the-art right now. We don't have as many galaxies that have been human-labeled, so let's use just a few of them and do transfer learning, which means you take the knowledge from the Exception neural net and tweak it a little bit so that it is now able to classify galaxies. And then we do a lot of different innovative applications on cosmology, like when you're doing transfer learning, we also do distributed training so that we accelerate this process. And then once we have processed these images, we now use them as training data sets to do recursive training to enhance the accuracy of our neural nets. And so we just finished this study. It has been accepted to Physics Letters B. And just to show you a plot, since this is an HPC conference, we were able to reduce the time for training from about 5 hours to 8 minutes, which is, I think, a first in cosmology. And this is without doing some additional data compressing. And those galaxies that you see there are galaxies that had not been studied in the DES survey, but with the neural net, we were now able to construct a catalog and provide the correct label for this. In different words, what we are doing is creating the data sets that will allow us to create galaxy catalogs for DES and for LSST in the future at a scale without using humans. So let me just conclude with this. I think we are at a crossroads right now. AI will continue to drive breakthroughs in the next few years. And I think it is a good time to start thinking about how we can reach convergence between AI and HPC in other domains. And I'm pretty sure that is going to happen based on the talk we had yesterday at dinner. Thank you.